Hi everybody. Today we're going to discuss empirical and molecular formulas. And so by the end of this, you should be able to use mass to determine a chemical formula. So first off, we need to know what molecular and empirical formulas are. Molecular formula, also known as a chemical formula, describes the exact composition of a particle. So it tells me exactly how many atoms of each element are present in a particle of that substance. An empirical formula is a little bit different. So an empirical formula is simply a ratio of the atoms of each element in the compound. So it's not the exact number, it's more of a comparative value. Empirical formulas can be determined by looking at data. In fact, that's what the word empirical means. It means derived from data. So empirical formulas can be determined by analyzing percent composition data. Why? Well, percent composition data is based on masses of elements that are present in a substance. So we can use those to help us determine the empirical formula. All we really need is mass. So to determine an empirical formula, the mass of each element must be given. If percentages are given, then use them as mass. So just pretend that they're grams. So if I have 40% carbon by mass and 60% oxygen by mass, so if the percent composition is given to me, just pretend that those numbers are masses, are grams. So it would be 40 grams of carbon and 60 grams of oxygen. Once you have the mass of each element, it needs to be converted to moles. And we've been using molar mass as a conversion factor to do this. Then what we're going to do is, after I have the number of moles of each element present in this sample, we are going to use the smallest number of moles to determine the ratio of particles in the compound. Okay, so basically what we need to do is we are going to look at all of our numbers of moles, so look at each element, and figure out which number of moles is the smallest. You're going to divide all of the amounts in moles by the smallest amount of moles. You'll see what we mean in a minute. From that ratio, we actually need to make sure that we get a whole number ratio, because the whole numbers are going to be used as the subscripts in our chemical formula, in our empirical formula. So here's an example problem. If we have a compound and it's found to contain 42.6 grams of oxygen, 32 grams of carbon, and 5.36 grams of hydrogen, we need to use that to determine the empirical formula. So in this case, masses were given to us. We don't have to turn percentages into mass. We can just use the masses as given. So I'm going to take that 42.6 grams of oxygen. And again, when we convert units, we draw our lines, drop our unit, and use dimensional analysis. 15.999 is the mass of oxygen from the periodic table. So 1 mole of oxygen is equal to 15.999 grams. I use that conversion factor to convert to moles. And so this comes out to 2.66 moles of oxygen. I do the exact same thing for the other elements. I had 32 grams of carbon, draw my lines and drop my unit. It's 12.011 grams on the periodic table for carbon, equal to 1 mole of that substance. And so again, I get 2.66 moles of carbon. For the last element, I'm going to take that 5.36 grams of hydrogen, draw my lines, drop my unit. The mass on the periodic table is 1.008. So 5.36 divided by 1.008 gives me 5.32 moles of hydrogen. So then the next step was to determine the smallest amount in moles. And so these two are actually the same, and they're the smallest, 2.66. So my smallest value in moles is 2.66. I'm going to divide them all by 2.66. When I do that, I get 1 for the first two. And when I divide 5.32 by 2.66, I get 1.99, which is close enough to round to the whole number 2. If you're within 2/10 of a whole number, you can go ahead and round it to a whole number. And so 1.99 is very close to the whole number 2. I'm going to go ahead and round that to 2. What does this tell me? That in my formula I have 2 hydrogens, 1 carbon, and 1 oxygen. So my ratio of elements is 1 carbon for every 2 hydrogens for every oxygen. And so the formula then, using those subscripts, would be C, we don't put a 1 as a subscript, H2, and then a single O. So 1 carbon, 2 hydrogens, and 1 oxygen is the ratio of elements in this compound. That would be my empirical formula. A molecular formula is a little bit different. We need to know the exact number of atoms in this compound. So the first step in determining a molecular formula is to actually figure out the empirical formula. We need to know the ratio of elements to each other first. We've already determined that. If you don't have the empirical formula, if it's not provided for you, then you need to use the data that's given to determine the empirical formula using that system we just went over. Secondly, the molar mass of the molecular formula will be given to you in the problem. You're going to divide that mass, the mass of your molecular formula, by the mass of your empirical formula. This indicates how many times larger the molecular formula is compared to the empirical formula. So we're going to figure out how many times bigger our molecule is than our empirical formula, than our ratio. Then we multiply the subscripts in the empirical formula by that factor calculated in step 2. The new subscripts represent our molecular formula. So on the next page we have an example. The molar mass of the compound from the previous example, so the real molar mass of this molecule is 180.18 grams per mole. That's its molar mass. Determine the molecular formula. Okay, well we know the empirical formula was CH2O. We already determined the empirical formula, so step 1 was done. We need to then take the mass of our molecule, 180.18, and divide it by the mass of this empirical formula. So if I add up the mass of this empirical formula really quickly, 12.011 plus hydrogen's mass times 2, 1.008 times 2, plus oxygen, I get 30.026. That's the molar mass of my empirical formula. So I need to take the molar mass of my molecular formula, 180.18, divide it by the molar mass of my empirical formula, and this will give me a factor. In fact, it comes out to a number very close to the whole number 6. What does this tell me? That tells me that my molecule is actually 6 times larger than my empirical formula. So if my molecule is 6 times larger than my empirical formula, I'm going to multiply my empirical formula by 6. If I multiply each subscript in this empirical formula by 6, I end up with the formula C times 6, C6, H2 times 6, so 2 times 6 is 12, O times 6, O6. So the formula for this compound is C6H12O6, which should look pretty familiar to you. That's the formula for glucose. Again, if I look at that, that is the real formula for my molecule. That is the molecular formula. Could that formula be simplified? Sure. The ratio of 6 to 12 to 6 could be simplified to 1 to 2 to 1. And that would be our empirical formula. Again, an empirical formula is sort of like a simplified molecular formula. It's a simplified ratio of elements. So this would be my empirical formula, CH2O, but my actual molecule is 6 times bigger, C6H12O6.